Hello everyone, let's continue with the series on electric charges and fields. We'll first study as to what is an electric field. It is defined as the region of space surrounding a charged body within which another charged body experiences a force is called as electric field of that body. To understand this, think of a charge Q1, and here is a charge Q2. Assuming that both the charges have same polarity, Q1 would exert a force on Q2, which would be a repulsive force. Similarly, Q2 will exert a force on Q1, even that also will be a repulsive force. Now, the question is, how does Q1 know that Q2 is present, or vice versa? How does Q2 know that Q1 is present? These charges cannot see each other, which means these charges are able to exert force by some mechanism, and that is called as electric field. The idea of field is a common word. Field doesn't only mean electric field. The idea of field is very common. Fields could be even gravitational fields. Fields could be even magnetic fields also. For example, think of two masses, say mass m1 and then mass m2, or assume that m1 is sun and m2 is like earth. We know that earth moves around the sun. There's a force which is acting between sun and the earth. So even earth is bound to sun. So even here also earth cannot see the sun and vice versa. But still a force exerts between them. Similarly, if we think of two magnets like north pole this side and then south pole this side, then the magnets would be pulled towards each other. Even here, the magnets cannot see each other, but between them a force exists. So in all the cases, it's very clear that there's something which is present, which is seen as force, and that is called as field. So it is the region of space surrounding a charged body within which another charged body experiences a force. So field is seen as force, or if force is present, it means field is existing. This is called as electric field. So it is an influence around a charge. And as seen earlier, the field is seen as force, or the force implies field is present. Electric field is a vector quantity, so it will have two things. One is the magnitude and direction. The magnitude is called as intensity or strength of the field. Many times you would find the word intensity in questions. So whenever the question says to find intensity, it implies to find the electric field's magnitude. I will define what this electric field is mathematically. So mathematically, electric field intensity or strength or field itself at a given point, that is, we have charge here, it is called as capital Q. We want to find out what is the field at some point P here. Let the distance between this point Q and this be P. Here it was something else here, because Q is the charge, and we'll call the points as point A and then point B. So at the point B, we need to find what is electric field. It is common sense that the electric field will decrease. Think of a source of bulb. For example, think like we have a source of bulb here, a source of light basically. We'll take few points called as point 1, point 2 and then point 3. It is common sense that when we go away from the source of light, the strength or the light what we get would be decreasing. The same here also. So away from the point A, the electric field will decrease. So we need to find what is Q. So we can't measure directly. So what we do here is, at this point Q, we bring in and place a charge, a small charge Q. This small charge Q has got many names to it. Some books called as unit positive charge and some books called as test charge. So basically it means the charge has a very small magnitude. So in this case, if you have charge Q, then the charge capital Q will exert a force on charge small q that we call as F. Now by definition, the electric field is defined as the force experienced between the charges by the charge what we have placed on the test charge. So E is defined as force by Q. It is very obvious that we should divide by Q, because what we want is, we want the effect only because of this charge Q. The form for force contains K, capital Q, small q by R square. We want something which is independent of the charge what we place here, or we want to find some parameter which depends only on this charge, not the charge placed here. So to remove the effect of this charge, we divide by the charge itself. It's again common sense. So E is given by F by Q. So we place a unit positive charge. This is called as electric field. If we write in terms of only magnitude, that is, if I write E is equal to F by Q, this is called as its intensity, because what we get here is only its magnitude. To summarize what we learned earlier, electric field is a vector quantity, and since E was defined as F by Q mathematically, remember we're defining E from here mathematically, so its dimension or SI unit would be Newton by Coulomb or Newton per Coulomb. And solve and see this, you would understand that its dimensions would be m power 1, L power 1, T power minus 3 and A power minus 1. We saw earlier that if we have a charge capital Q at a point A and at a point P, at a point B where we need to find the electric field, we place a test charge. So here this charge, because of which, or the charge whose field we want to find, that charge is called as source charge, and the charge which we place to find the field, which has a very small magnitude, is called as test charge. So source charge is a charge whose field we want to find, and test charge is a charge which we place. The next thing is, if you look at this point B, at this point B, we need to find only the charge A's electric field. But here what will happen is, if we place a charge small q at this point B or close to point B, somewhere here close to point B, even this also will contribute its own field. So physically what will happen is, at this point B or close to point B, we'll have two contributions. We'll have this contribution which is more dominant, and then this is very small, but still this will contribute also, which means effectively or practically the field what we find very close to point B or at point B is not the exact field because of charge capital Q, rather it is a combination of fields because of charges capital Q and small q. To remove the effect of small q, we should ensure that that small q is very small. Mathematically, we can define E to be more precisely as E is equal to, it is force by Q, but we want this Q to be very small. So mathematically, I can say E is equal to force by Q as limit of Q tends to 0. It means the value of Q is very close to 0. The smaller the value of Q is, the more would be the contribution of charge capital Q. So you would find even this also in many big books. So the idea here is we should ensure that the charge Q is so small that its contribution is negligible or it is 0. So that at a given point, the field what we find is because of the source charge only. Next concept is to find how would the electric field be, because we saw that electric field would have direction as well as even its magnitude. So here we need to find its direction. First, what we'll do here is to find direction, we'll take a charge. Let's assume we take a positive charge whose value is called as capital K. At some point here, I need to find its direction. So what we do in this case is we bring in a test charge called a small q and find the force at this point. We know that the force would be a repulsive force because what we have here is a positive charge which is q, and remember, by convention the small charge is always a positive test charge. That's how we define this. It is a positive test charge. So it will be a repulsive force. So E is given as F by Q. Now since this Q is just a number, just a positive number, the direction of E is same as the direction of F. In this case, since F is in this direction, that's how even field also will be. If we take some other point, a point somewhere here, so at this point if you want to find the field, again what we do is we bring in a test charge which is same as small q and we find the force at this point. The force here will be a repulsive force because both are same polarity. So at this point also the field would be same along that of force only. So if you do it for all the points, surrounding charge, we get something like this configuration. So for a positive charge, we get a configuration which goes out like this. Now here, if we put a circle around it, it's in 3 dimension, so there we would get a sphere, but in 2 dimension we'll get a circle. So if you put a circle around this, then what we get here, the condition where each of these arrows is like a radius vector, because for a sphere the radius vector is normal to the sphere. So we say that for a positive charge the electric field lines are radially outward. It is radially outward. That is because what we get is a radius vector for a given sphere. For negative charge, we can do the same thing. Let us think of a charge which is minus q. Again here also we want to find what is the field at a given point. Let that point be P here. Same as the previous case, at this point P we place a test charge which is positive. Since the charges have different polarity, the force will be an attractive force. So force would be towards the bigger charge or the source charge. It's an attractive force. So even here, the electric field is same as the direction of electric field is same as the force direction. So in this case, the field will be towards the charge. If we do it for all the points, it is something like this. Even here, as seen in the previous case, if we draw a circle around this point, then what we get would be something like this. So here it is towards the charge. So in this case, we say for a negative charge, the electric field lines are radially inwards. So for a positive charge, it was radially outwards, and for a negative charge, it is radially inwards. Now we'll try to find out what is the electric field for a point charge in terms of Q, K, and then R. That is, if you have a charge here called as capital Q, at this point P, let this point be A, this point be B, and let the separation between the two charges be some R. So we need to find what is the field at this point R. Let the distance between these 2 points be R. Now as we saw earlier, we should bring in a test charge small q and find the force on this test charge. So force on this charge would be K capital Q small q by R square, and then the force would be going out like this. This is what force would be. So if you want to give direction to it, F would be along AB. Electric field was defined mathematically as the force by the charge what we're placing, that's a test charge, so by Q. In terms of magnitude, you can write only magnitude as E is equal to F by Q, that is equal to Q, K capital Q small q by R square, the whole by small q. So from this, small q gets cancelled, and what remains would be E is equal to K Q by R square. In vector form, if you want to give direction to it, in vector form, this is along AB because it is radially outwards. This is the expression for electric field due to a point charge, where, just to recap, K is equal to 1 by 4 pi epsilon naught. Imagine a case where we have more number of point charges or a single charge. As given here, we have a charge Q1 which is positive, charge Q2 which is positive, and again Q3 and Q4 each is positive. We need to find what is the field at this point P. Do remember that each of this charge will create its own field. Let the field which the charge Q1 creates be called as E1. So it is vector E1 here. Since we learned that for a positive charge, the electric field lines would be going out radially, the field from the charge goes out. Similarly, the field because of charge Q2 is called as E2, which is outwards radially, even E3 and then E4. In this case, we need to find the total charge, the total electric field. So the total electric field is given as the vector sum of each field. So in this case, since we have 4 fields, it will be vector sum of 4 fields, and this is called as principle of superposition of electric fields. In simple terms, this tells us that the net field or the total field at any point is equal to the vector sum of individual fields. This is a very important principle because based on this principle, there will be a lot of numericals. The next topic is uniform electric field. As the name tells us, uniform means something which is same. But recall that field is a vector quantity. This will have both magnitude and direction. So we can say if at a given points or if at all the points, the magnitude and direction are same, then such a field is said to be an uniform electric field. As given here, we will see what these are in the later topics. For now, think of a arrangement where the field lines are parallel to each other. If you take any point, if you take a point somewhere here, call as point 1 or a point 2, take any points anywhere at all these points 1, 2, 3 and 4, the electric field would be same in magnitude and direction. Such fields are called as uniform electric fields. Let us go back and see, does the field or is the field created by positive charge and negative charge, is it uniform or not? To recap the formula, we look at a positive charge first. In this case, we just now solved that the electric field is equal to kq by r square. Now we'll take few points here. We'll take a point, say 1 at this point and a point 2 somewhere here. It is very obvious that from points 1 and point 2, the fields are different. Since point 1 is close to the source charge, the field at point 1 would be greater than the field at point 2. So this cannot be a uniform field because the fields are varying. If you look at any points on the circle, a point here, a point here, on the sphere in 3 dimensions, it is circle in 2 dimensions. In this case, at all these points, we'll call as say point A, point B, point C. At all the points, the distance remains same. So, at the points A, B and C, the electric field will have same magnitude, but these will have different directions. So at point A, the field goes out like this. It goes out like this at point A. Similarly, at point B, it goes out like this. So they are different directions. Hence, a single charge, whether it is positive or negative, cannot create an uniform electric field. As seen earlier, we found out that the electric field is given as k q by r square. We'll find out what does this field depend on. It's given from here that it depends on few factors. If you expand this, it becomes 1 by 4 pi epsilon naught. It is q by r square. So it's very obvious from here that the field doesn't depend on the charge what you're placing. So the field depends on only the source charge for a given medium. For example, think of air or think of any medium. For a given medium, it depends only on 2 factors. It depends on what is the source charge itself and distance from the source charge. So when you go away from the source charge, the field will decrease. Theoretically, the field would be 0 only if r tends to infinity, because mathematically putting q as 0 is meaningless. So E is 0 when r tends to infinity. So only at very far away distances, the effect of field would be 0. Next is physical significance of electric field. We realize now that electric field is the most important quantity for a given charge, and this field is the one which causes force. So we'll find out what is its significance. First and foremost, the electrostatic energy is stored in the field. Second point is, this field is responsible for interaction between charges. We saw this earlier, that field is the one which causes force. So without the field, the charges will not know that they are present. For example, if you have charge capital Q and this charge creates its own field everywhere. It creates fields like this everywhere, it creates a fields. Suppose if you bring a charge somewhere in this field, if you bring a charge somewhere here, I bring a small charge Q, even this charge will have its own field. If this charge is having small magnitude, it will have its own field at this point. So what is happening here is the fields of the two charges are interacting. So basically, force is nothing but interaction of two fields. That is what is force. So basically, when we say force, it means it is interaction between two fields. That's the point given here. The first point says the energy is stored in the field. To make more sense out of it, let us think an analog of this. Let us think of an example of Earth's surface. Like we'll call this as Earth's surface, and somewhere here at a given height of example, think of a tree somewhere here, and then a fruit is hanging from a tree. Think of a fruit like this. Let the height of this fruit be h from the reference point or the Earth's surface. Let its mass be m. So we learned in first year that its potential energy, which is called as U, is given as m into g into h. Now what is understood is that students think that the energy, which is mgh, is present in this mass. That's not actually correct. This energy mgh is present in the field between the two masses, because here what we get is gravitational field. So the energy is stored in this gravitational field. It is not in the mass, it's in the system, it's in the field. To summarize the earlier concepts, we will take a few examples as given here. Example 1 says 2 point charges of value 2 into 10 power minus 7 coulomb and 1 into 10 power minus 7 coulomb are placed 0.01 meter, which is 1 centimeter apart in vacuum. What is the magnitude of electric field produced by either charge at the position of the other charge? Now to understand this, let us take two charges placed at some distance. We'll call the charge here as point A, this as point B. The charge here is 2 into 10 power minus 7 coulomb. The charge here is 1 into 10 power minus 7 coulomb. We have two charges and distance between them is given as 1 centimeter. So question says, what is the magnitude of electric field produced by either charge at the position of the other charge? We need to find what is the field which charge at A creates at point B. Similarly, we should find what is the electric field which charge at point B creates at point A. So we'll first look at charge A and the field what it creates at point B. We'll call that as E suffix A. So E suffix A is the field which charge at point A creates at point B. A charge at point B cannot create this field because at that point field is not defined. Because if you look at E is equal to K Q by R square. At the charge itself, R is 0. It means E tends to infinity, which is meaningless. So electric field at a given charge at the given point at itself is meaningless. That is, the field which A creates at itself is meaningless. So at point B, we'll have only one contribution, which is because of charge kept at point A. So this is equal to, using the form given besides, it is 9 into 10 power 9 into Q is 2 into 10 power minus 7. It is R square. We can write 1 centimeter as 10 power minus 2 whole square, because 1 centimeter is 10 power minus 2 meter. This is equal to, it is 18 into 10 power plus 2 from this by 10 power minus 4 becomes 10 power plus 4. It becomes 18 into 10 power 6 Newton per coulomb, or you can write this as 1.8 into 10 power 7 Newton per coulomb. The direction, if you want to find out, then EA would be 1.8 into 10 power 7 Newton per coulomb. Since it is a positive charge, the field would be going out radially, that is equal to the value given here along AB. Similarly, let's find out, so this would be EA. Similarly, let's find out what is E suffix B, that is equal to, which is basically the field which charge at point B creates at point A. That is equal to 9 into 10 power 9 into charge here is only 10 power minus 7. So 10 power minus 7 by distance square, which is 10 power minus 2 the whole square. That is equal to, it will be 9 into 10 power 6. As seen earlier, Newton per coulomb. This field would be going away from the point A. So at this point, the field would be in this direction. We call this as EB. In vector form, you can write this EB as 9 into 10 power 6 Newton per coulomb. It is along BA. Example 2 says, calculate the intensity, which means it's only its magnitude, of the electric field at a point of 3 centimeter distance from a point charge of 5 microcoulomb. This is straightforward. Electric field is given as K Q by R square. K is 9 into 10 power 9. Q here is 5 microcoulomb. It is 5 into 10 power minus 6 by 3 centimeter. It should be 3 into 10 power minus 2 the whole square. It is equal to, it is 9 into 5 into 10 power plus 3 by 9 into 10 power minus 4. So from here 9 gets cancelled. So what remains would be 5 into, it's 10 power 3 here because it's 9, 10 power 3. So 10 power 3 plus 4 by 10 power plus 7. 10 power plus 7 Newton per coulomb. Example 3 says, two charges of magnitudes plus 9 nanocoulomb. Nano means 10 power minus 9 and plus 4 nanocoulomb are placed at the corners A and C. So observe the corners carefully. It is A and C of a right angle triangle ABC, in which AB is 3 meter, BC is 4 meter and CA is 5 meter. Find the magnitude and direction of the resultant electric intensity. It says intensity, which means only the magnitude at the corner B. So first and foremost, we'll try to draw a diagram for this. And what is given here is a right angled triangle, something of this kind. This is what is given in the question. We'll mark the points, but be careful with the points because they are different lengths. First and foremost, look at the larger side, which is 5 meter. It would mean that if we call this as point A because it is CA, then this should be point C. So we'll put point C somewhere here. So AC is 5 meter and this should be point B. So we need to find the magnitude and direction of the resultant electric field at the point B. So the charge at point A is 9 nanocoulomb. The charge at point C is 4 nanocoulomb. So we'll find what is the net field at the point P. So in this case, we will use the principle of superposition of electric fields. That is, we will find what is the electric field because of charges at point A and point C which creates at point B. So we'll first find the field which charge at point A creates at point B. Since the charge at point A is a positive charge, the field will be going out radially. So it goes out like this. We'll call this as E suffix A. Similarly, the charge at point C is again a positive charge. So even this will create a field. That field will go out from the charge. So it goes out like this. We'll call this charge or this electric field as E suffix C. So we need to add the net field. The net field, which you call as E, the net field would be given as EA plus EC. This is what is called as principle of superposition of electric fields. We'll first find what is EA. So EA is equal to, it will be K Q by R square. So K is 9 into 10 power 9. Q here is 9 into 10 power minus 9 because it's 9 a coulomb by R square. Recall what is AB. AB was given as 3 meter and BC is given as 4 meter. We put it back here by 3 square because it is in meter only, by 3 square, which is same as 9. So this 9 and this 9 gets cancelled and 10 power plus 9 and this 9 gets cancelled. Finally, what remains is electric field at A is 9 Newton per coulomb. In vector form, it is along AB. It is away from A and going away from B also. Let us find what is EC. EC is equal to the same form, which is K Q by R square. K is 9 into 10 power 9 and Q here is 4 into 10 power minus 9. My distance is 4 square, that is 16. So from here 1 4 gets cancelled because it is 4 by 16 and also 10 power plus 9, 10 power minus 9 gets cancelled. So finally what remains would be EC in vector form would be 9 by 4 Newton per coulomb and it would be along CB because it is a positive charge. We need to find the net electric field and you know that for any two vectors the resultant is given as under root of A square plus B square plus 2 into A into B into cos theta. So here theta is the angle between the two vectors. In this case, theta would be this angle here, which is 90 degrees, and cos 90 is 0. So finally what you get from here would be E is equal to, it will be EA the whole square plus EC the whole square plus 2 into EA into EC into cos 90. That is equal to, it will be 9 square plus 9 by 4 the whole square under root. That is equal to, it is 81 plus 81 by 16 under root. That is equal to, it will be 81 plus this term here would be 5.0625. When you solve it further and see, if you put the values of this, add it and solve it, then what we get would be E is equal to 9.27 Newton per Coulomb. So this is the required electric field. And that field, if you want to find direction of it, again use parallelogram law and find it. Use the form tan alpha is equal to B sin theta plus A plus B into cos theta, and solve it. You get the answer to find the resultant direction also. Thank you.